Okay, so part 2 on thermochemistry, starting to look at the enthalpy of formation, and this is getting into the Hess's law like we did in the lab, and this starts on page 6 of your outlines. So there are data tables in the back of your textbook. There's also one on page 255 of your textbook that looks at the standard enthalpy of formations for different compounds. And the main thing you need to realize is that this is looking at 1 mole of a compound from its element in their standard state of if you take those elements and you form a compound, how much energy is required to form that compound. One thing that's really going to help you is that just like when we were assigning oxidation states, if it is an element by itself, then its delta H is also going to be 0, just like we said its oxidation number was 0. So that will help you a little bit in doing these equations. So, you know, we're still dealing with standard temperature and pressure in terms of, well, not the standard state of 25 degrees Celsius, 298 Kelvin, 1 atmosphere, 1 molar concentration. The worksheet calls this the Big Mama equation, but this is Hess's law. Hess's law looks at the delta H of the reaction equals the sum, and that's what this symbol means, the sum of the delta H of the products minus the sum of the delta H of the reactants. So we're looking at products minus reactants. All right, for exercise 8, all right, we have a list that has your delta H's already listed for you for these substances. And it says, given the above information, calculate delta H of the reaction for this whole chemical equation. So the first thing you've got to do is look and see if there's any of them that are just elements by themselves that can be crossed out. So aluminum is that. That's a 0. We don't have to worry about it. And that's it. All of the others are actual parts that actually you're going to have formation, heats of formation. So we're going to have to use all of those. So we look at our equation, and the equation that we're going to use is that Hess's law equation looking at, okay, well, it's the delta H reaction equals the sum of the delta H of the products minus the sum of the delta H of the reactants. Okay, so products minus reactants. Well, all we've got to do is we've got to start looking at this. What this means, okay, if we're looking at the sum of the products, well, all of these are our products. So we have Al2O3 plus AlCl3 plus 3, because we have to look at how many moles of each thing we have, 3 NOs plus 6 H2O. So those are our products minus the sum of our reactants. And in this case, we only have one reactant. There's 3 of them, though. NH4, ClO4. Okay. So now all we've got to do is go back and put in the numbers that stand for this. All right, Al2O3. Well, we come up here and we find Al2O3. It has a delta H of negative 1,676. So negative 1,676 plus AlCl3, a minus 704, plus, and we've got 3 of these, so be sure to do 3 times NO. NO is 90, plus 6 times H2O, and H2O is negative 242. So the sum of all that minus 3 times the NH4ClO4, which is this first one, which is negative 295. All right, so you're going to have to put all of this into your calculator. Negative 1,676 plus a negative 704 plus 3 times 90 plus 6 times minus 242 minus 3 times negative 295. When you work all of that out, you get a negative 2,677, and this is kilojoules per mole. So our delta H of the reaction, the whole reaction, is equal to negative 2,677 kilojoules per mole. And since it's negative, it is an exothermic reaction. Remember, a negative delta H means an exothermic. Okay, exercise 9 down here. Sometimes you don't have all of the values. So we've got this reaction here, and if we look at it, we can automatically already say that's a 0 because it's an element by itself. And you're looking at this, and then it says the heat of formation for the substance sometimes has to be calculated by working backwards from its heat of combustion. And it says calculate the delta HF, so the heat of formation of C6H12O6 given the combustion reaction above, along with the following information. So we want to know, okay, delta H formation for this reaction is equal to the sum of the products minus sum of the reactants, which equals delta, well, we look at the products here, okay? Well, products is 6CO2 plus 6H2O minus the reactant. In this case, there's only one, and that's C6H12O6. Well, it gave us the delta H of formation of the whole thing. That's what this is. This is our delta H for the reaction. It is 2,800 kilojoules. It is on the product side, which means that this is a negative delta H because it's an exothermic reaction. That is being given off. So that's exothermic. So our delta H is going to be negative 2,800 kilojoules per mole. Actually, I should have put that there, negative 2,800 kilojoules per mole. So let me just scribble that out. Equals 6 times, actually I didn't need to scribble that out, sorry. It's equal to 6 times CO2. CO2 is negative 393.5 plus 6 times water, which is negative 285.8 minus, and this is the one that we want to find. We want to find C6H12O6. So we want to solve for that. And the way to solve for that is to take it over on the other side of the equation. So C6H12O6, so it's no longer negative. We made it positive because we added it to this side to get rid of it. So we bring it over to this side. We take this negative 2,800, bring it over to the other side to add it. So we get the 6 times negative 393.5 plus 6 times their negative 285.8 plus 2,800. When you calculate that, you get negative 1,276, and this is the same as the previous one, kilojoules per mole. So that's our delta H of formation of C6H12O6. Exercise 10. You're dealing with a reaction that happens when you mix powdered aluminum and iron together and ignite it. So this is a combustion reaction. Said using enthalpies of formation, calculate the standard change in enthalpy for the thermite reaction. So you actually have to look in the back of the book at the table for the formation. And we're looking for delta H of your reaction. And that's going to be, if we look up in our equation, well, that's an element, so that's 0. That's an element, so that's 0. So we're just looking at this minus this. So our product, Al2O3, minus our reactant of Fe2O3. So if we look up those numbers in the back of the book, we get that Al2O3 is a negative 1,676. And the Fe2O3 is a negative 826. So this winds up being a negative 850 kilojoules per mole. So delta H for the reaction. So that one was not difficult. It's just they did not give you the actual numbers. You had to look it up in a table. You know, on the AP test, they're going to give you those so that you'll have them to look up. All right, so enthalpy. Now, this is the Hess's law that we were talking about. So Hess's law. If you find a combination of chemical reactions or that add up to give you your desired equation. So this is just like the lab that we did Tuesday and Wednesday of last time, that we were looking at Hess's law, and we were trying to find the overall heat for the release that was released when you burn magnesium ribbon. And so we used the other two reactions that you did with the calorimeter to be able to figure out how much heat overall was released. So, you know, with Hess's law, we've already talked about this, but you have to decide how you're going to rearrange your equations so that the reactants and products are on the right side of the equation. Typically for these Hess's law equations, they're going to give you the desired equation that they want you to go for, and you've got to figure out how to add those together to get the heats to work out correctly for you to be able to calculate. If you have to reverse an equation, also remember you have to reverse the delta H. So be sure you remember this. This one is a big one. If you reverse the equation, you have to reverse that. Also, if you have to multiply in order to get the coefficients to work out, then you also have to multiply your delta H. Or if you have to divide, you also have to divide your delta H. And then be sure that everything checks out, cancels out, and gives you the exact equation that you're wanting. All right, so for exercise 11, it says calculate delta H for this overall reaction. This is your goal equation. So this is what we want. This equation is what we want. And we're going to use these three equations to get there. So we've got to look at, okay, well, we want H3BO3 to be on the reactant side. Well, this first equation, we have H3BO3 on the reactant side. So that equation's okay. We know it's going to stay in the same direction. Also, we want B2O3 to be on the product. Well, we have to look and find an equation that has B2O3 in it. Well, here it is. Here's B2O3, and it's on the product side. So we're good. Water also has to be on the product side, so we've got water. Now what you've got to look at is, okay, well, I've got this compound here, this H2B4O7, that's not in my goal equation, which means I've got to get rid of it. Which means that I've got to somehow figure out how to get rid of that. Well, if I have it on this side of this equation that I know is in the right direction that I want it to go, then that means that I've got to flip this equation. So this one is going to be flipped, so that my H2B4O7 is going to be on the other side of the arrow so that I can cancel out. So let's rewrite these. So we have H3BO3, and that yields HBO2 plus H2O. We also have, this is the one that I'm going to flip, so I need to say 4HBO2. Line your arrows up again like we did when we were doing redox. It just makes it neater. H2B4O7 plus H2O. And then this one's going to stay in the same direction. H2B4O7 to B2O3 plus H2O. Okay, so now we've got to look at, okay, well, we've got these equations. Here's that H2B4O7 that I can cancel out. I can get rid of that automatically because it's on opposite sides of the equation. Now, I've got my H3BO3 where I want it. I've got my B2O3 where I want it. But I've got to get rid of this HBO2. And the easiest way to get rid of that is I've got to get my units to equal. So I need to multiply everything in this by 4 so that my units will balance out and I can cancel them. So now I've got 4 HBO2, so I can cancel that, Now I've got everything where I need it to be, so I just need to write it out. I've got 4 H3BO3. It's going to give me 2 B2O3 plus I have 4, 5, 6. Those waters add together, so I've got 6 waters. Okay, well, if I look at my goal equation, that is 2, nothing, and 3. And I have 4, 2, and 6. So everything's doubled. So I'm going to have to cut all of that in half. I'm going to have to divide that in a minute. But let's go ahead and tackle our numbers over here about the delta H's. Okay? Well, remember that if you flip an equation, you have to flip its charge, its sign. So we flip that sign. And anything that we do to an equation, we also have to do to the delta H. So this first equation, we multiplied it by 4. So that means I've got to multiply that by 4. So this winds up being negative 0.08. This is a plus 11.3. And that's also a plus 17.5. So when I add that all together, I get 28.88. And that's kilojoules per mole. Well, you know, I said that we've got too much here. We've got twice as much as we need. So we need to cut all of this in half. So that's going to just get rid of it. And that's going to be a 3. So now we have 2 H3BO3, B2O3, and 3 H2O, which is our goal equation. But I had to cut all of that in half. So that means that I've also got to half this delta H. So when I do that, it's going to be half of this 28.88. So my delta H is now 14.44 kilojoules per mole. So the main thing that you've got to remember is that whatever you do to the equations, you also have to do to the delta H's. So if you multiply, you got to multiply those. If you divide, you got to divide those. Okay, the big thing about bond energies here, we're almost done. The thing about bond energies is that you need to realize that in order to break or form bonds, you have to have energy. So energy is going in to break them, energy is being released to form them. So endothermic is when you're breaking the bonds, that is taking energy in. Energy is released when they're formed, that's exothermic. So a good way to kind of think about this is that when you break these bond energies, this is like the cost. How much is it going to cost you to break those bonds? And this one is like, okay, well, we've broken those bonds, we've paid some money or paid some energy. What is our payoff? What are we going to get out of it when we form those bonds? So it's going to cost us something, but we're also going to get something back in return. So here we go with exercise 12. Calculate the change in energy that accompanies the following reaction given the state below. You've got hydrogen plus fluorine gives us hydrogen fluoride. So you're breaking bonds and forming bonds, and the bonds that you're breaking are these hydrogen-hydrogen bonds, the fluorine-fluorine bonds, to be able to make an HF bond, because those are diatomic molecules. So you can kind of think of it as, okay, you've got this HH bond plus this FF bond, and you're going to make HF bond, and there's two of those. So that's what's happening in this equation. So this hydrogen-hydrogen bond is 432. This FF bond is 154. So that is what it's costing us. That's the energy to break those. And then this is what is required, or what your payoff is going to be, is 565. When we form this hydrogen fluoride bond, that there are two of them, so that's 2 times 565. So that is, if you add 432 plus 154, that gives us 586. And 2 times 565 is 1130. So, you know, remember, this is our payoff. This is the energy we're getting out of it. This is our cost. How much is it costing us energy-wise to break those bonds? So, if you look at your our delta H is the energy broken minus the energy formed. Okay, so that would be 586, that's the broken, minus the energy formed, which is 1130, which equals negative 544 kilojoules per mole. All right, so that's a negative exothermic reaction. And the way you can kind of think about it is, if your reactant's energy is less than your product's energy, then that's an exo. And then the reverse would also be true. All right, so summary here. What's this really telling you about the changes in energy? Well, if delta H is positive, it's an endothermic reaction. You had to take in energy to be able to make that reaction work. If the delta H is negative, then it's exothermic, which means the energy was released from the reaction. And so that should be easy for you at this point. Surely by now we've kind of hammered this in, that delta H is positive for an endothermic and delta H is negative for an exothermic. So you've got to get that into your head. Quick little sketch of what's going on. You have energy over time. Well, if your energy equation, the graph of it, looks something like this, where you've got your reactants here and products here, and you're looking at the amount of energy that is required. Well, if you compare that to this graph, where here is your reactants, here's your products, and your energies are very different. Here you're starting out with a fairly high amount of energy for your reactants, but your products are at a much lower energy. There's been a big release of energy. So this is a negative delta H. This is an exothermic reaction. It's given off heat out of the system, and the products are at a lower energy level. This one, the products are at a higher energy level than the reactants. So this is a positive delta H. So this would be an endothermic reaction where energy had to be put into this to make it, the products be at a higher state of energy than the reactants. And that is the end of this video, and we'll talk about more later.